Hi, and welcome to the first lecture of the Qiskit Global Summer School. I am honored to be able to deliver the first lecture in a series of 2 weeks of lectures from IBM contributors. My lecture today is going to focus on the foundations of quantum mechanics. We're going to talk about the history of quantum mechanics, how it came to be, how it was discovered, who discovered it, and when. And then we're going to sort of gently merge into the future and talk a little bit about where this field is going. My name is Olivia Lanes. I'm the global lead for education and learning here at IBM, and let's get started. So in the beginning, in the pre-quantum era, classical physics reigned supreme. Scientists confidently relied on the foundations laid by Newtonian mechanics, Maxwell's electromagnetism, and believed that these theories could describe the universe completely. Newtonian mechanics, illustrated by simple systems such as inclined planes and pulleys, successfully explained everyday motions and forces. Objects followed predictable trajectories governed by clear laws. Similarly, Maxwell's equations elegantly unified electricity, magnetism, and optics. Phenomena like electromagnetic waves propagating through space seemed thoroughly understood. Yet, by the late 19th century, some scientists famously declared, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." A pretty unmotivating statement overall. However, this confidence overlooked subtle anomalies at atomic scales, problems that classical physics couldn't explain. These unresolved mysteries would soon open the door to quantum mechanics, revolutionizing physics forever. Let's explore some of these first anomalies. As is often the case in science, the most exciting discoveries begin to happen when nature stops behaving the way you expect. Seemingly wrong experimental results give way to deeper exploration and understanding. One such example of that is the very cool-sounding ultraviolet catastrophe circa the 1900s. From classical thermodynamics and electromagnetism, Lord Rayleigh and James Jeans derived a formula that predicted just how much radiation black bodies of different wavelengths would give off, where here I is the intensity, lambda the wavelength, T the temperature, K is the Boltzmann constant. Now, this formula worked really very well, except for when lambda went to 0, wavelengths in the ultraviolet range. The intensity was predicted to go to infinity. This implies that a black body would emit infinite energy at high frequencies, and obviously that's not what experiments showed. Experiments showed that radiation intensity increases with a frequency up to a peak, and then it drops off at shorter wavelengths, the ultraviolet and beyond. So the classical model matched at long wavelengths, but failed dramatically at short ones. Then Max Planck came along, and he tried to force-fit theory to experiment and stumbled upon a radical idea. Energy is not continuous. It's emitted in discrete packets, or quanta, and he introduced this formula shown here, E equals h nu, where E is the energy of a quanta, nu is the frequency of the radiation, and h is Planck's constant, which is a new fundamental constant. Now, at the time, Planck didn't really assume that this had any deeper meaning. He just found a way to make the equation work and assumed it was, a cool little math trick. And even the best physicists do this at times. But as hindsight is always 20/20, we now know that this was really our first glimpse into quantum mechanics and using it to make much more accurate predictions about the world. Now let's move on to another extremely famous experiment called the photoelectric effect. The photoelectric effect is the phenomenon where light shining on a metal surface causes electrons to be ejected from that surface. This was first observed in the late 19th century and systematically studied by Hertz in 1887 and later Philip Leonard in 1902. Under classical wave theory of light, here's what physicists expected to happen. First, that light intensity, or the brightness, should control how much energy electrons gain. 2, there would be a delay. Electrons would gradually soak up the energy and then eventually be ejected. And 3, there would be no threshold frequency. Even low-frequency light, if it was intense enough, should eventually cause the electrons to be ejected. So in short, brighter light equals more energy, regardless of the frequency. However, experiments showed the exact opposite. Electrons were ejected instantly, no matter how dim the light was. The ejection only happened if the light's frequency was above a certain threshold, and increasing intensity at low frequencies did nothing. Lastly, increasing the frequency, not the intensity, increased the electron's energy. This could not be explained by classical wave theory. So, that's when Einstein stepped in. You've probably heard of him. Einstein proposed a radical idea, that light isn't just a wave, it comes in particles called photons, each with energy proportional to its frequency. Remember this equation from a few slides ago. He suggested that one photon hits one electron. If the photon's energy is greater than the work function phi, the energy needed to liberate an electron from the metal, then the electron is then ejected. Any extra energy becomes kinetic energy for the electron. He came up with the photoelectric equation shown here. K max equals h nu minus phi. K max is the kinetic energy of the ejected electron, phi, the work function of the metal, and then h and nu we've already defined previously. So looking for experimental confirmation of the theory, that happened in 1914 by Robert Millikan, who initially tried to disprove it, but instead ended up providing the strongest evidence in its favor to date. The kinetic energy of the electrons increased linearly with frequency, not intensity, and the slope of that line was measured experimentally to be Planck's constant, measurable and consistent. Einstein actually won the Nobel Prize for this work in physics in 1921, not for relativity, as many people think, but for explaining the photoelectric effect. So in the end, a lot of people like to say Einstein hated quantum mechanics, and maybe there's still some truth to that, but he also had a really big hand in shaping it as well. Now let's keep going, staying in chronological order. In the early 20th century, the classical models of the atom, like the Rutherford model, couldn't explain why atoms were stable or why they emitted light at only specific wavelengths, like those seen in hydrogen spectrum, for instance. And yet, scientists were seeing it again and again, the exact same wavelengths. Taking hydrogen as an example, they saw that light was only emitted at very specific wavelengths, like the ones listed here. They just didn't know why. And then Niels Bohr came in and he said only certain discrete or quantized orbits allowed for electrons. His key postulates were that electrons orbit the nucleus in specific energy levels or shells without radiating energy, unlike classical theory, which would have predicted that the electrons spiraling into the nucleus would be always emitting energy. Energy is only absorbed or emitted when an electron jumps between these levels, as crudely shown by this diagram here with these different colors. The energy of the emitted or absorbed photon corresponds to the difference in energy between the different levels. So here, the energy of the photon would be En minus Em, and that equals h nu, where En and Em are the energies of the different levels, which we can label as 3, 4, 5, 6, and so on. His theory ended up predicting what we kept observing for hydrogen really, really well. However, there were a few issues. For one, it only worked well for hydrogen, which has a single electron, so maybe that's not so surprising. But it couldn't explain the fine structure or the electronic spin. We ended up finding the reasons for this even later on. Now, coming off of the success of that experiment, de Broglie proposed a somewhat radical idea at the time, that if light can behave like a particle, then particles, like electrons, should be able to behave like waves. De Broglie proposed that any moving particle has an associated wavelength given by lambda equals h over p, where lambda is the de Broglie wavelength, h is Planck's constant, and p is the momentum of the particle, just m times v for non-relativistic speeds. This means that faster moving particles have shorter wavelengths. Heavier particles also have smaller wavelengths. But for macroscopic objects like a baseball, lambda is incredibly small and undetectable. That's why we never see baseballs exhibiting wave-like properties, for instance. But for tiny particles like electrons, the wavelength is measurable and it matters. The de Broglie hypothesis was spectacularly confirmed by the Davison-Germer experiment, and this experiment was as follows. Electrons were fired at a nickel crystal and then scattered. The scattered electrons created interference patterns that were measured with a detector, just like waves diffracting through a grating. And from this, they were able to conclude that electrons were behaving like waves, not just like particles. And this was a turning point. It validated the idea that matter has wave-like properties and helped usher in the formal development of quantum mechanics. Before this, particles were thought of as little solid objects. But because of de Broglie's idea and its confirmation, they showed that electrons and all particles, really, can exhibit interference and diffraction, which are inherently wave-like phenomena. And that the wave associated with a particle is not a physical ripple in space, but rather a probability wave, which is a central idea that was formed later in the Schrödinger formulation. Now, this is when quantum mechanics sort of faced a turning point. In 1925, Heisenberg introduced what we call matrix mechanics. This was the first complete and consistent mathematical formulation of quantum theory. What Heisenberg proposed was radical at the time. Instead of trying to track particles through space, like in classical physics, and measure their trajectory at different points, he suggested using matrices. Yes, those things from linear algebra, to represent observable quantities like position and momentum. One of the key insights here is that in this formulation, position and momentum don't commute. That is, when written as matrices, x times p does not equal the same as p times x. Instead, they follow this commutation relation, where those two square brackets indicate a commutation relation, and for x and p, that equals I h bar. Now, a commutation relationship is defined as two operators, a times b minus b times a. If it is 0, we say that the operators commute, and they can be observed precisely simultaneously. But if they don't, well, it gets a little bit more complicated. And this isn't just some quirky mathematical fact. It's deeply tied into the uncertainty principle. It tells us that we can't precisely know both the position and momentum of an object at the same time, which is a sharp break from classical thinking. You can visualize this in part with the figure on the right. Each row in the image represents a different quantum state. The left plots in red show the uncertainty in the particle's position, and the right plots in blue show the same for momentum. Basically, how many possible different values there are for momentum in the position the particle could occupy. At the top, momentum is shown very precisely, and we can be extremely confident when we measure its value because the peak is so narrow. But for position, for the same measurement, the spread is quite large, and we can't isolate exactly where the particle is located. And then the opposite is true for the bottom images. When we know exactly where the particle is, we can't precisely measure the momentum. These diagrams show that both of these non-commuting operators, position and momentum, cannot be measured definitively at the same time. When we're sure of position, we are unsure of momentum, and the opposite is true as well. Heisenberg also gave us this eloquent equation of motion, rightly named the Heisenberg equation of motion, which is shown here, where A is an observable that we can measure, like position or momentum. Now, this is revolutionary because it replaced Newton's equations with something operator-based, again emphasizing that quantum theory is about how observables evolve in time, not about particles following a specific path. Now, just a year later, Erwin Schrödinger introduced wave mechanics, where particles are described by something called wave functions, usually written as psi of x or psi x and t, if dependent on time. This is actually what's being plotted on the previous slide. A wave function psi is a mathematical function that describes a quantum system's state. It encodes everything that we can know about a particle, like an electron or a system of particles. At its core, the wave function tells us the amplitude for finding a particle at a position x. But because the wave function is a complex valued function, meaning it can contain imaginary numbers, it's not directly observable. What we can observe is actually the probability, which is the modulus of psi of x squared. That's the probability density of finding the particle at a position x. Now, Schrödinger's equations looked very different, but strangely, the results agreed with Heisenberg's. So the big realization here was that both matrix mechanics and wave mechanics were mathematically equivalent. They're just two different mathematical representations of the same theory. Now, at this point, I actually want to take a short break from our history lesson and talk about the first key component of quantum phenomena that makes quantum mechanics so unusual, and that's the principle of superposition. Now, Heisenberg didn't explicitly talk about superposition, but his use of matrices to describe transitions between energy states involved adding contributions from different states. For instance, a rule that we learn in linear algebra that applies here is that if psi1 and psi2 are both solutions to this equation, in this case the Schrödinger equation, then their sum is also a solution. He sort of made note of this in his work and mentioned mixed wave states, but the implications of this weren't really examined until a bit later. Now, I want to discuss the principle of superposition with one of my favorite experiments as an illustrated example, the double slit experiment. The first double slit experiment was actually done over a century before, but it was a classical physics experiment done with light. The experiment was done much later with electrons. So for those who may not be familiar with this iconic experiment, the setup is this. There exists a source of particles. Here I've just created this purple box, and for all intents and purposes, it's capable of sending out one particle at a time. There's also a film in the path of the particles with two holes cut in it. The sizes are created and adjusted so that it's physically possible for the particle to pass through either hole and then be measured by a detector or a screen on the other side so you can visually see which hole the particle went through, allegedly. So during the experiment, what has to happen is this. First, one hole in the film is blocked off somehow so that the particle really has no choice but to go through the other hole. I've shown here only the particles that make it through the second hole, but if there were more particles streaming out of it, they would just get blocked at the first. So they make their way through the other hole, and then they would form a normal distribution on the measurement screen. And this makes good intuitive sense. And then we do the same thing with the other hole. We block off the second and let particles fly free, and some will make it through the first hole. And we would also see a normal distribution where the width of the distribution just corresponds to how large the hole is. Nothing weird happens until we open up both slits at the same time. What everyone at that time expected to see was just the two distributions at the same time instead of one. One for each slit, but still localized and still centered between the holes. Maybe they would have, a little overlap here. But that's not at all what was seen. What was actually seen and I apologize for my crude hand-drawn but fairly accurate squiggle here, is an interference pattern with many troughs and peaks centered about the middle of the slit, where there actually wasn't even a direct path for the particles to go through. Now, how could this be? How does this make any sense? Indeed, it is not obvious or intuitive how to interpret this. Well, probably to no one's surprise, the only way to do this accurately is through the lens of quantum mechanics, specifically hitting our first key quantum principle, superposition. If we were to write the mathematical expression, the wave function, that represents what's going on here in the picture, we would say that the wave function is equal to 1 over root 2 of the left hole plus the right hole. To calculate the probabilities, we would have to square the whole wave function, take the modulus, which would give us a value of 1/2 for each possibility, meaning they are equally likely and the superposition is even. The particle would then have a 50-50% chance to go through each hole. However, since both are solutions, the linear combination of both possibilities is actually also a solution. So in the end, there's no other option but to say that the particle actually somehow went through both holes at the same time. And this is an image of what we would actually see in reality if we measured it in a lab. One other interesting aspect to note here is that the interference pattern that appears on the measurement screen is only visible when we don't track which path the particle actually took. If you follow actual particles' trajectory with your eyes, or if it's even just possible to calculate it mathematically and backtrack it, then the interference pattern literally disappears, and we see the original predicted shape of the two distributions, which is wild, right? This is a great example of what people refer to as the measurement problem in quantum mechanics, but neither you nor I are going to be able to solve that one right now. Now, another key quantum phenomena that arises from superposition in the same experiment is quantum interference, which is basically the idea that these particles don't behave like tiny little marbles like we want to imagine. They behave like probability waves that can interfere with one another or even themselves, which is how we end up with such a weird-looking interference pattern on the other side. Personally, this visual here helps me feel a little bit better about the interpretation of the object, somehow passing through both holes at once. Because if we picture them as waves, and if we picture them instead as a wave source with the waves expanding outwards, it becomes much more believable, at least in my brain. Now, the interference pattern clearly shows both constructive and destructive interference. Constructive interference happens when the wave functions combine and amplify. That's how we get these peaks. It increases the probability of finding a particle at that location. Destructive interference is the exact opposite. That happens when wave functions overlap in opposite phases, reducing or even completely nullifying the probability of detecting the particle in that space, and that's where these troughs occur. And remember, remarkably, this interference pattern emerges even if particles pass through one at a time, underscoring the quantum nature. Each particle is actually able to interfere with itself. So in summary here, superposition is not just a mathematics trick. It's a real physical state where the particle isn't in one place or the other, but kind of both at once until measured. It proves that quantum systems behave fundamentally differently from classical ones. And it also plays a crucial role in quantum algorithms, as we'll see later on. It allows quantum algorithms to amplify the probability of correct answers and cancel out the wrong ones through careful manipulation of quantum states. All right, we're done with that short interlude for now. Let's rejoin our quantum timeline. Now it is 1935, and time for the publication of one of the most influential papers in physics of all time, the EPR paper, named for Einstein and his colleagues Podolsky and Rosen. Its full title is can quantum mechanical descriptions of physical reality be considered complete? Question mark. The EPR paper challenges the completeness of quantum mechanics, but not its correctness. Here's the gist. Quantum mechanics predicts that two particles can become correlated in such a way that measuring one instantly determines the state of the other, even if they're really, really far apart. We now call this entanglement, but Einstein at the time famously called it spooky action at a distance. This suggested that either information is somehow traveling faster than light in between the two particles, which violates special relativity, which says nothing can travel faster than the speed of light, or the particles had pre-existing properties, and he called them hidden variables that quantum mechanics didn't account for. Therefore, the EPR authors concluded quantum mechanics must be incomplete. There must be some deeper theory that restores local realism, the idea that physical properties exist independently of observation and that nothing is influencing anything else faster than the speed of light. In response, Erwin Schrödinger wrote a paper agreeing with Einstein that quantum theory implied something very strange. And in it, he coined the term entanglement, or in German, I'll do my best to pronounce this, Verstrickung, meaning something like intertwining or linking together. He declared that entanglement was the core mystery of quantum mechanics. And the significance of all of this was that we finally recognized that entangled systems behave as a single quantum object, no matter how far apart their individual components were. And you'll note here, unlike on every other slide, I don't have an image to show you because personally, I hate all visual representations that people have come up with in order to show entanglement. And yes, I'm being a little silly, I'm being a little tongue-in-cheek here. But anything that I could show you would in some ways be false or at least misleading. And that's why so many people hated and still don't like the idea of quantum mechanics, including Einstein. And that's why so many people try to argue with me and my colleagues online or in YouTube comments. To some, it is just very unsettling that there's not an accurate picture that you can visualize for what's going on. And there's no good metaphor that accurately describes it either. I guess once you get to the point in your career, or you've just been studying it for quite a while like we have, you kind of just get over that. I'm sorry that's not more satisfying, but it remains very cool nonetheless, and also extremely useful. Now, a few months later, Schrödinger responded to the EPR paper. Schrödinger proposes the idea of Schrödinger's cat, a thought experiment to illustrate the bizarre consequence of superposition and entanglement. In 1936, follow-up discussions were had where Schrödinger continued to explore entangled systems. Schrödinger agreed what EPR described was weird, but he disagreed that it meant that quantum mechanics was wrong and incomplete. Instead, he thought it revealed something fundamental about quantum systems. It was so profound because entanglement meant that quantum reality is inherently non-local. A measurement on one particle can instantly affect the other, even across the world or the universe. Schrödinger realized this was not a side effect or a quirk, it was an essential feature of quantum theory. If we're talking about entangled electrons, for instance, which is what is shown here mathematically, and what has come to be known as a Bell state, we see a state described where neither electron individually is in a definite spin state. The pair together has a perfectly defined relationship where if electron A is measured to be up, electron B will instantly be found to be down. If electron A is measured to be down, electron B will instantly be found to be up. Before measurement, neither electron has a definite spin, only the entangled combination is well defined, kind of like the idea of the cat in the box, where we don't know if it's alive or dead until we open the box and that measurement has been made and that measurement defines the state of the cat. The system as a whole has a definite property, but the individual parts do not. And so psi x of A and xb cannot be separated into its individual components. And you can see this in the first equation because no single component here can be factored out of the parentheses. Now, after the intense philosophical debates of the 1930s, EPR, Schrödinger's cat, most physicists stopped kind of worrying about quantum weirdness. Instead, they adopted what we call a shut up and calculate attitude. And this is something that's told to many young physicists in their quantum mechanics classes at some point, one or another. They used quantum mechanics to make precise predictions. They stopped debating its philosophical implications. And really, this approach kind of worked. As a result, there were tremendous advances in understanding atoms, nuclei, and fundamental forces. For instance, QED was invented, quantum electrodynamics, and it's the quantum field theory that describes how light or photons interacts with matter, charged particles like electrons and positrons. It's one of the most successful and precisely tested theories in all of physics and science. Richard Feynman introduced Feynman diagrams, as shown here, a visual shorthand for calculating interactions in QED, now standard across particle physics. At its core, QED says that charged particles emit and absorb photons, which are the force carriers of the electromagnetic interaction. These processes are probabilistic and governed by amplitudes, not certainties. And lastly, interactions can be calculated using these Feynman diagrams, each representing a possible path particles can take. And like I said, QED is one of the most accurately tested theories in physics. For example, the anomalous magnetic moment of the electron, a small deviation from what you would expect classically, has been predicted and measured to an agreement of more than 1 part in a trillion. There are not very many theories of nature that come even close to that. The development of quantum mechanics was also crucial to the advancement of nuclear theory in the 30s and the 40s. Without quantum mechanics, scientists wouldn't have been able to understand how nuclei are structured, how they behave, or how to manipulate them in reactions like fission. We have now arrived in the 1960s. Quantum mechanics has become incredibly successful at predicting experimental results. QED has made astonishingly precise predictions, such as the electron's magnetic moment and the Lamb shift, with experimental agreement to parts per billion. The impact of this was that quantum theory wasn't just weird. It worked better than anything else. Scientists stopped doubting its correctness and focused on using it. To set the baseline, now the question became not whether quantum mechanics is correct, but again, what does quantum mechanics actually say about reality? Physicist John Bell formalized the argument into a testable mathematical inequality called the Bell inequality. It basically stated that if experiments violate Bell's inequality, local hidden variables cannot explain quantum mechanics. And surprise, surprise, this was eventually tested in the laboratory, and when these experiments were done, carefully and correctly, of course, they were all found to violate the inequality. I'll dive more into these details in just a second. But the overall message was this. Bell turned philosophy into experimental physics, which is just so cool. It became possible to test the fundamental nature of reality, and quantum mechanics could be tested against what we might call common sense, local realism, and possibly be shown to violate it. Now let's turn to one of these key results in the foundations of quantum mechanics and the Bell's inequality, the CHSH inequality specifically, named for Clauser, Horn, Shimony, and Holt. This inequality is a testable version of Bell's theorem, and it gives us a way to experimentally decide. The experiment aimed to answer the question, is the world governed by local hidden variables, or does quantum mechanics really allow for non-local correlations? Here's the very basic setup. We have two entangled particles sent to two distant observers, commonly called Alice and Bob. Each can choose between two measurement settings, say A or A prime for Alice or B prime for Bob. This could be measuring different directions or alignments of the particle. But each experiment yields a binary result, either 1 or -1. Now, if the world were governed by local hidden variables, meaning each particle carries pre-programmed instructions and no faster-than-light influence is occurring, then there's a strict limit on how correlated Alice and Bob's measurements can be. Again, assuming nothing else. The limit is expressed by the CH-SH inequality shown here, where the terms E of A and B are the quantum correlations of the particle pairs, where the quantum correlation is defined to be the expectation value of the product of the outcomes of the experiment. This value must be less than or equal to 2, assuming nothing else, just locality and realism are the only things in play. But here's the kicker. Quantum mechanics predicts violations of this inequality. It actually predicted that we will measure not 2 or less, but 2 square root 2, which is about 2.8. Obviously higher than 2. This is beyond anything any local theory could produce. And it's been confirmed in dozens of experiments, including loophole-free tests in recent years. So what does this mean? It means that nature doesn't obey local realism. There are no hidden variables that determine outcomes in advance while keeping everything local. Instead, entangled pairs are deeply connected in a way that defies classical explanation. And yet, they still don't allow faster-than-light signaling. And this isn't just a philosophical result. These non-local correlations are now resources in quantum cryptography, quantum networks, and even device-independent quantum computing. The CH-SH inequality draws a line in the sand, and quantum mechanics steps over it. And actually, you're going to have a chance to do just the same in the first lab assignment of the summer school. It's really cool, and the fact that you can do these kind of experiments now, just from your home with Qiskit, it blows my mind a little bit. And if you're interested in learning more about Bell's tests and Bell's theorem and how the Nobel Prize in Physics was awarded just a few years ago for demonstrating these results, I encourage you to take a look at one of my other videos on the channel called Bell's Inequality, the weirdest theorem in the world. And this actually brings me almost to the end of what I wanted to cover in today's lecture. But before we end, let's now briefly talk about the birth of quantum information science, a pivotal shift that began in the 1990s. This is the era when researchers stopped asking, why is quantum physics so weird? And started asking, how can we use that weirdness for something useful? In 1994, Peter Shor and Love Grover proposed groundbreaking quantum algorithms. Shor's for factoring large numbers exponentially faster than classical computers, and Grover for searching through unsorted databases quadratically faster. And these weren't just theoretical curiosities. They revealed that quantum mechanics could be computationally useful. And then in 1996, David DiVincenzo clearly laid out a set of criteria that any physical system would need to satisfy in order to serve as a quantum computer, one capable of actually running Shor and Grover's algorithm. It talked about initializing qubits to implementing gate operations and then error correction. Around the same time, experimentalists were making early progress towards realizing qubits in the lab, using systems like trapped ions and superconducting qubits. So what was the impact of all of this? A mindset shift. Scientists began to see that quantum weirdness was not a bug, it's a feature. Instead of resisting entanglement, superposition, uncertainty, they started engineering around them, laying the foundations for the quantum technologies that we're building today. And like Newton once said, if I have seen further, It is by standing on the shoulders of giants. And us working in the field of quantum information are indeed standing on the shoulders of some of the most important and impactful scientific giants to ever live. This field directly builds on centuries of physics, and the 1990s marked the moment where we began to harness those ideas, not just to describe the universe, but to compute with it and understand it even better. And now it's your turn. And here's the best part. The story is not finished. It's still being written in code, in labs, in theory, and in lectures and stories like this one. The next Shore or Grover might be turning into the summer school right now. I hope they are. All right, so now we're really at the end here. If you weren't familiar with this long history of quantum mechanics and quantum physics, and surely I missed some things and I didn't touch upon every single experiment, I hope you at least enjoyed some of this walkthrough about some of the major discoveries that happened in the past century. And if you were already familiar with most of this, I hope you still enjoyed reminiscing and pausing to gain a bird's eye view of how far we've come. And I know I did. Thanks for watching, and make sure you tune in tomorrow for the next lecture of the 2025 Qiskit Global Summer School. Thanks.